So number 6 is asking or stating that parallelogram ABCD in the XY plane with vertices given is transformed according to the relation. What we're asked to do is, using those transformed coordinates, find the volume of find the volume between Z equals 1 and the area of the XY plane bounded by the parallelogram ABCD. Okay, so that's a typo bonus for somebody. Anyway, so we're looking to transform our coordinates. The Z is not going to be relevant because we're transforming within the XY coordinate system beneath a plane that is parallel to the XY coordinate plane. So we're not concerned about any kind of movement and how that would impact the overall volume. So let's work on the conversions first. Let's pop it all in. For the sake of, I mean, it's really dependent on how you like to do things, but for the sake of efficiency, you could use a linear regression, but you know, when you're dealing with just pairs of points, sometimes it's just easier to go and do it by hand. All right, but in terms of a visual, it might be a good idea to at least get a plot going. Okay, so I would want to be looking for, and we could label it up, but in the order in which I put them in is the order that they were given, A, B, C, then D. So in a counterclockwise fashion, actually that would be clockwise fashion. So I would be looking for the equation of the line passing through AB, then BC, then CD, then D back to A. Knowing that in a parallelogram, opposite sides are parallel to one another, the plot actually helps us in a reasonable way come up with the slopes, just make sure that there isn't anything fishy with the scale. Right? But we have a rise over run of 2 over 2, right? So up 2 over 2, so that makes things easy. So the slope here is equal to 1, so CD is going to have the same slope. Then from 3, 4 to 6, 5, change in y over change in x is going to be 1 over 3, so up 1 over 3, or just 1/3 as the kids say these days. No, I don't even know what I'm saying sometimes. So let me give myself a little bit more room to roam here. So I could write this as y equals 1 times x minus 1 plus 2. From B to C, y equals 1/3 times x minus 3 plus 4. From C to D, y equals 1 times x minus 6 plus 5. Just grabbing a point that you know is on the line and putting it into the point slope form. And then y is equal to 1/3 x minus, it doesn't really matter, I'll go with the D value, so 4 plus 3. Alright, you can clean it up a smidge, not really, I mean we can get it into slope intercept, we can get it into standard form, so many different possibilities. So y equals x minus 1 plus 2, so y equals x plus 1, y equals 1/3 minus 1/3 x minus 1 plus 4, So y equals 1/3 x plus 3. Y equals x minus 6 plus 5. So y equals x minus 1. Y equals 1/3 x minus 4/3. So y would be equal to 1/3 x minus 1 1/3. And just adding 3 to the negative 4/3. All right, you can double check these equations on Desmos and make sure they go through the appropriate coordinates. So that's what I'm going to do real quickly. Just for the sake of having less to type in, I'm going to write it, well, we'll also need this for another step in a minute, but I'm going to write this as y minus x equals 1. I'm going to multiply everything by 3 here. So that'll make that 3y equals x plus, looks like 9. All right, so that's going to be 3y, sorry, minus x equals 9. For this one, I will actually write it as y equals 1/3 x minus 4/3 first. Multiply both sides by 3, just like I did above. This one's easy. This is just y minus x equals -1. And then this one, we just kind of smidge everything over. Or maybe just reduce it in size. I don't want to go off the page. All right, so 3y equals x minus 4, which makes 3y minus x equal to 4. All right, so I'm just going to pop all these in real quick because I think it's just a little easier to type in. So y minus x equals 1. All right, that's a good fit. 3y minus x equals 9. Also good fit. Y minus x equals -1. 3y minus x, oops, equals a 4. All right, so that one's off. Okay, I messed something up here. All right, so let me just take a quick look. Just going to do that real quick. -4/3 plus 3. Oh, okay, yeah. Little snafu on that one. That should have been 5/3. That is my bad. Yeah, because that's 1 2/3 is what it should have been. Oh, you know what? I think in my mind I zigged when I should have zagged. All right, so what can you do? What can you do? All right, so 5/3. All right, so then this will be a 5. I mean, just by eyeballing it on the graph, I probably could have just figured that out, but, you know, because it seemed like it was about a unit down from where it ought to be, but we just do it algebraically, make the correction. Okay, so now what we need to do is define our u's and v's. So that's given by the transformation equation, so we know that x is equal to -3/2 u plus 1/2 v, and we know y is equal to -1/2 u plus 1/2 v. All right, so we have two relations. One involves y minus x and the other involves 3y minus x. So let's see what that looks like in terms of u's and v's. All right, so we'll do y minus x. All right, so that's going to be, and I'll just duplicate this. Here's my y. Here's my x, and I'm subtracting. So if I subtract I'm negating each part. I'm going to resize again. Oh, that I don't want to take. All right, so negative 1/2 u plus 3/2 u is 2/2 u, which is 1 u, so u. And then 1/2 minus 1/2 v, well, 1/2 v minus 1/2 v is 0. So this whole thing, y minus x, is actually going to end up equaling a u. That's great. That's great news. So now we know by substitution that u, by this substitution, that is, u equals 1 and u equals negative 1. All right? So that's information. And so when we look at the graph, the u, well, let me just highlight the appropriate ones. I'll turn on the appropriate ones. These two parallel lines, the bounded region is in between those two. All right? So we would actually be looking at something that would look along the lines of u such that u is bounded between negative 1 and 1. So we'll hang on to that piece of information for a sec. We also know that 3y minus x is a relation. So let's actually figure out what 3 times y minus x is. All right. So we did y minus x. So what we would do is actually not too much different from what we already did, except we're going to triple the first equation, or well, it's still an expression. Now it's an equation. All right, so we're going to triple that. So when we distribute, it's going to make this a 3. So 3/2. All right. So we're looking at, so now this is gone when I distribute it. Negative 3/2 u plus 3/2 u is going to go to 0. 3/2 v minus 1/2 v is going to be equal to 2/2 v. So that's the same as saying 1v, or just v. All right, so now I would look at where v would be equal to 9 and 5. Well, we'll put the 5 first. So v is equal to 5. V is equal to 9. So we would be saying our bounds for v would be v such that v is in between. I keep writing the v first. Well, u first and the v first. 5 to 9. So that's great news, because we just took something that was a parallelogram in the xy coordinate system and transformed it into the uv coordinate system. Still 2 dimensions. U is going to go from negative 1 to 1. It just kind of split up on me. So 1, 2, 3, 4, 5. Okay, so 1, 2, 3, 4. Last two took off on me. All right, so 1, 2, 3, 4, 5. 6, 7, 8, 9. Roughly around right here. I'm just kind of ballparking it. Obv. U equals 5. U V is equal to 5. V is equal to 9. U is equal to negative 1. U is equal to positive 1. All right, so it's just this little interval here that I'm concerned with. All right. So if I were to write the double integral to find the volume underneath z equals 1, under ordinary circumstances, that would be the double integral over some base region of z dx dy dy dx. Well, let me just write dA. All right. So what we did was we transformed this to the UV coordinate system. So instead of dx dy, I have du dv, or dv du. It doesn't make a difference because it's a rectangular base region. I can go either way. All right. Now, since z is parallel to the xy plane, it's uniform in the sense that we're looking at something that is not going to change in height. Right? So the only thing we would need is a correction factor to get us from the unit area, unit basis of the xy coordinate system to the basis of the UV coordinate system. All right. So what I would need to do is figure out the Jacobian for this new coordinate system. All right. So we have the equations, the vector function that allows for the transformation, but we can use those equations to get us the basis area of the UV coordinate system. So I'm going to rewrite my equations, x in terms of u and v, and we're going to take the Jacobian, we're going to look for the Jacobian determinant, but let's find the Jacobian matrix. J sub f. So we're differentiating x with respect to u and with respect to v, and then doing the same thing with the y's. All right, so we're looking at, with respect to u, the v's are irrelevant, so -3/2, -1/2. Then with respect to the v's, the u's are irrelevant, so 1/2, 1/2. So I need the determinant of that. All right, so we really are, I mean, we're finding the Jacobian matrix first, but then we are finding the determinant of that Jacobian matrix. The determinant of the Jacobian matrix making the Jacobian, or Jacobian determinant. All right, so resize, diagonal down, diagonal up. We are looking at -3/4 on the downswing, on the upswing, minus negative, so +1/4. So that's going to be -1/2. But we want the absolute on that. All right, which is going to be a 1/2. All right, so what that's telling us is the transformed unit vectors from the xy coordinate system to the UV coordinate system, where they would have an area, that basis vectors, the 1, 0, 0, 1, when they're transformed into this new system, that new basis area would have a value of 1/2. All right. In comparison to the 1, it's 1/2 of the whatever the corresponding areas are in the xy coordinate system. All right. So that gives us a correction factor. All right. So what that tells us is that if we have a dy dx, to convert that over into du's dv's, I would just have to attach a multiplier of 1/2. All right. So then it just ends up being a matter pause for dramatic effect One of these days I'll time the talking better with the writing, because that's what happens. Is like, oh, is he going to say something really important? No, not any more important than what I was saying prior to that. But now we can substitute in the substitutables and go from there. So I'd be looking at the outer integral. The bounds are 5 to 9. That's the v. All right. So uv, vu doesn't make a difference. But since I wrote it in this order, the outer ones would go from 5 to 9. The inner ones would go from -1 to 1. Z was the constant plane 1 multiplied by the 1/2 du dv. So now we have a complete unit change, coordinate change. So it's actually pretty not bad to do it even by hand. So I'd be looking at the inner integral. So the antiderivative of 1/2 would be 1/2 u on the interval of -1 to 1. So that's 1/2 times 1 minus 1/2 times -1. So 1/2 plus 1/2 is going to be equal to 1. So then we're going to integrate that over the interval of 5 to 9. So v over the interval of 5 to 9, 9 minus 5, because straight substitution is going to be equal to 4. So we're looking to construct a vector field for this lattice of points, having the vector equation 1, comma y. So what I'm going to do is I'll just put all the points there indicated based off of the lattice, the little x values that are indicated on the graph. But we're going to plot only 1, comma y. So for every one of these y values, we're only going to plot the number 1 for the corresponding value of x. Oops, meant to copy that. So in the case of a variable x value, it's a little bit more complicated, but here the vector field is only going to vary based off of the y coordinate. All right, so at -1, 1, we're going to plot the vector 1, -1. All right, so 1, -1 looks like this. That's what we're going to plot at -1, 1. No, at -1, -1. All right, at -1, 0, we're going to plot 1, 0. So here's 1, 0. That's what we're going to plot at -1, 0. At -1, 1, we're going to plot 1, 1. So 1, 1 would look like this. That's going to get translated right on over to -1, 1. All right. At 0, -1, we're going to plot 1, -1. All right. Now, all right, so just look at it the rest of the way. And this is what makes this a little bit nicer than some of the other problems that we've had to do. No matter where you are in terms of x, the trio of y values are always going to remain the same. All right. So at 0, -1, 0, 0, and 0, 1, it's still the same trio of vectors. So we do a quick copy paste job here. And then that would be the same for the positive ones. So number 8, a plate is in the shape of a quarter circle and has vertices given. on the xy plane, it has a height of 1 meter along the z-axis. So we're looking for the density. Oh, I'm sorry, no, we're not. The density is defined by this equation, find the total mass. All right, so density, rho, right, so that's the density. A lot of people will use a capital D in this context for density just because we're using rho for spherical coordinates. So you can keep that in mind, but if we may not have that conflict, so we can just kind of leave it as is. So anyway, that's equal to mass over volume. All right, so if we're looking for mass, that's equal to density times volume. All right, so if we wanted to figure out mass, we already know how to find volume in a bunch of different ways. Compute the volume, incorporating the density function, and we'll have the total mass. All right, so the plate is in the shape of a quarter circle that has these vertices. All right, so that's in the xy plane. So 0, 0, 0, 0 pi, pi 0, and it creates a quarter circle. Okay, so we have that. A height of 1 meter, all right? So if we're going up the z-axis, that's going to create a quarter of a circular disc going up 1 meter, all right? So something to keep in mind. That has a cylindrical feel to it, all right? So if we go into the 3-dimensional coordinate system, if we're looking at, oh boy, if we're looking at the xy plane, here's pi, pi, and we'll call this 1. We have our quarter circle, and we have our height of 1, if I can make that stick. Let's see. Close enough. Oh, undo. Just kind of put a few of them here. Kind of make it look nice. Best I can anyway. Alright, so we're looking for this volume, and then we'll incorporate the value or the density function into this. Now it's a quarter of a circle with height, so it's a cylinder. Alright, so cylindrical coordinates seems to make the most sense here. Alright, so the volume in cylindrical coordinates, so we'll just focus on that. Radius of 1, so 0 to 1. Only going out from 0 to pi over 2. Oh, sorry, radius is pi. Apologies. I saw that z equals 1 and I went after it like an animal. All right, so, but 0 to pi over 2, then we'd have z multiplied by r dr d theta. But what we're going to do is now incorporate the density model. All right, so we're going to take this and multiply it by the rho value. I'm not going to use rho, I'm just going to write in the sine of x cosine of y. Just because if I get the rho in there, I'm worried that people are going to think spherical coordinates when you're reviewing your notes. Kilograms per meter squared, and then multiplied by r dr d theta. All right. And so we're in kind of a little bit, we'll call it a pickle. I like pickles. All right. So we have a function that's in terms of x's and y's and r's and thetas here. All right, so we can go after this a couple of different ways. One would be converting the sine and cosine functions over into cylindrical coordinates. The other would be to go the other way and convert all the cylindrical stuff into rectangular coordinates. So you can go either way. You wouldn't be wrong if you went in either direction. For sine, well, we know sine is equal to y over r, so you can make that substitution, but it's sine of theta, not sine of x. All right, but we do know that x is equal to r cosine of theta, and y is equal to r sine of theta. All right, so we can make that substitution. We know z is going to be equal to 1. They told us that. Height of 1, that's not changing. So we'd be looking at 0 to pi over 2, 0 to pi, sine of r cosine theta, and then cosine of r sine of theta, r dr d theta. All right, so that's one possible way to go. All right, technology-wise, I mean, to integrate this, it's going to be pretty beefy. All right, so let's go after it a different way, which is to say, all right, so we got, if the question just asked us to write the integral or sum of integrals that could be used to find the volume, or in this case the mass, then this would be fine. All right, but we need to get an answer here. So let's do it in rectangular coordinates. If I write this equation for the quarter circle, it would be x squared plus y squared is equal to pi squared, which I can then solve for y is equal to plus or minus the square root of pi squared minus x squared, for quality 2. And so that'll give me the lower and upper bounds, but I don't need the lower bounds. I would only be going from 0 to that. All right, so I could say the double integral in terms of x, I'm only going out as far as pi. All right, because it's still the same distance in terms of x. In terms of y, I'd be going from 0 to the square root of pi squared minus x squared, and then we'd have z dy dx, and then we would make those, you know, the same substitutions that we did previously, replacing the z with a 1 and including the sine of x cosine of y. So integrating with respect to y first, I would get sine of y. So we would be looking at sine x, sine y over this interval. The 0 would be irrelevant, so then I would be looking at going from 0 to pi and integrating sine of x, sine of this, which we could do on the calculator. You know, Desmosify this bad boy. So 0 to pi sine x. I had stats for some reason. Then sine square root pi squared minus x squared. Close it up. Twice slap on a dx. Not a d, whatever that was. And you get about 0.9-ish, approximately 0.9, and it's a measure of mass. So kilograms makes sense.